Okay, cool, thanks. So this is the statement for the third problem where Farmer John starts with a permutation of length P, and what will happen is he'll generate a new sequence H, which is generated in the following way. So first he'll compare the first and the you'll compare the first and the last elements of P, and depending on whether or not if the first element is larger, he'll write down the second element in the permutation and remove the first element. Alternatively, if the last element is greater, he'll write down the second to last element and remove the last element. And in the end, farmer reverse John will have written down n-1 integers, which are the hints in that order. And then now, given the array of hints, farmer John wants us to construct a permutation that's consistent with the hints given. And out of all the possible permutations, we want to construct the one that's lexicographically minimal. um, Meaning that like at the first location that they differ, the at the first position where two permutations differ, the one with the smaller value will be lexicographically smaller than the other one. So yeah, so this is the problem. And before we get started on solving the problem, or before we get to the solution, there are a couple observations that we have to make about the hints that are given. Yeah. So the first observation is that the last element in the hint must be one. This is because the number one can never be removed from P, as whether or not it's P1 or Pn, it'll never be the larger of the two. So since the number one will never be removed, on the second to last or on the very last comparison, one will be left behind and it will certainly be written down. The second observation is that the number one can occur twice, but not more. And the reason it can occur twice is that if there's an element both to the left and to the right of one, both of them will be removed eventually, right? Since one is the last number that'll be removed, they both get removed. And when the element on the left is removed, one will get written down. And when the element on the right is removed, one will also get written down. So the number one can occur twice. And it can also occur once. Or and also but alternate but no the number one cannot occur more than twice. And the third observation is that no number other than one can occur more than once. And the reasoning for this is similar. It's because a number can be written down if there's an element on the left that will be removed, or if there's an element on the right that will be removed. But the number one will either be on the left or on the right. And if the number one is on the left, then the number to the left of our current number will never be removed because one will never get removed and it'll never reach that eventually. So for instance, if you consider the example I have down here, if you consider the four here, right? One is to one is to the left of it, and this one will never get removed. So no matter what happens, four will only get written down at most once because when the two is removed, we'll write down four. So yeah, but by similar logic, no number other than one can occur in H more than once. So the next observation is that if an element is missing from H, uh, so like H consists of the numbers from 1 to n, right? And if an element is missing from H, it is either P of 1 or it is P of n. And the reason for that is that those two elements will never get written down, right? Because you can write down P of two, you can write down the second element, you can write down the second to last element, and you can write down all the numbers in the middle, just eventually. But you'll never write down the two numbers that are on the endpoints themselves. So if an element is missing from H, it is either it is one of the two endpoints. So these observations, well, in particular the first three observations, also give the conditions for whether or not a solution exists. If no element occurs more than once, except one, of course, one occurs exactly once or exactly twice, and the last element is one, a solution exists. Otherwise, the solution does not exist. So then there are two cases to consider in our solution. The first case is when the number one occurs once at the last as the last element in H, and the second case is when the element one occurs twice. So if the number one only occurs once, that means there's only the only permutation elements are to the right of it, or there are only permutation elements to the left of it. Because this means that because if there are permutation elements on both sides of one, that means that one would get written down twice, right? Because when the number to the left is removed and when the number to the right is removed, they'll both result in one getting written down. But since one only occurs once, we know that one of those two cases won't happen. So there's only elements to the left of it or only elements to the right of it. And then since we want our array to be lexicographically minimal, one must be the first element in P. And the reason for that is that if P of 1 is equal to 1, that is automatically lexicographically smaller than if P of 1 is equal to n, or P of n is equal to 1, and P of 1 is equal to something else, because 1 is the smallest number there is, at least the smallest one that we care about. So this means that the missing number in the array, the h has length n minus 1, so there's exactly one number missing in the range of 1 to n. That element must be the last element in P, because this is related to the fourth hint, right? We know what P of 1 is, so the missing element has to be P of n. And then, but this also means that, so if we consider simulating the process, right? We know that the last element is greater than 1 because everything is greater than 1. So we know that the first number written down has to be the second to last element in P. So we know that h of 1 must be the second to last element in P. We know that h of 2 must be the third to last element in P, and so on, until we write down all the numbers up until h of n minus 2. And then we can skip h of n minus 1 equals 1 since we know where the 1 is. And with this, we can generate the entire permutation. And then in the example I gave, we can find that the final permutation will end up being 1, 2, 5, 4, 3, uh, which I did not write down. Yeah. So that's the case where the number 1 only occurs once. So then if 1 occurs twice, we know that there's two missing values. This is because there's a total of n minus or yeah, there's a total of n minus 2 elements that are not no, there's a total of n minus 3 elements that are not equal to 1. And then there's one of them that's 1, which leaves two elements that are missing. And let's call them A and B, and we assume that A is less than B. If they weren't, we can just swap them. To make the array lexicographically minimized, we would want P of 1 as A and P of n as B, because A is less than B, and having P of 1 be A will be better than having P of 1 be B, right? So then if we consider the process, of writing down elements, we'll compare P of 1 and P of n, since we know what both of them are, and depending on the answer, we can remove one of them and write down h of 1. So for instance, if P of 1 is greater than P of n, then we know that the first hint, h of 1, has to be the second element, P of 2. And we know that P of 1 was removed on the first step. And similarly, if P of 1 is smaller, then h1 is P of n minus 1, or the second to last element, and P of n was removed. And with this process, we'll always know what the first and the last element are, and we can simulate the entire process and we can use this method to place all the elements in P. Since there are a total of n minus 1 minus 1 equals n over 2 in H, other than the last one. Wait, no, no, yeah. The total of n minus 2 unfilled elements in P are, yeah, it's n minus 1 minus 1 because the last number being 1 isn't helpful. So that leaves n minus 2 elements that will fill in. There's a total of n minus 2 unfilled elements in P. So this algorithm will certainly fill in all the elements in P. So like one of the important like overarching themes is that after the first two elements are fixed, the process to determine the rest is fixed. So the lexicographically minimum condition only really applies to the first element and the last element in the permutation. The total complexity is O of n per test case, which will pass under the constraints that are given. And there's a bit of implementation for this problem. It's possible to make some bugs. So there's sample code provided in the paste-bin link. And yeah, that's all there is for problem 3. So if I remember correctly, I'm also going to do like a rough overview of the USACO contest or of this particular bronze contest. And I think the most important thing for this contest is that since this contest is 5 hours long, the problems did end up being harder, especially in problems one and three, and even in problem two, a lot more emphasis was placed on writing good long code, uh, like as opposed to some of the previous contests. Like for instance, problem one is very implementation heavy for a bronze problem, and problem two and problem three are both on like the above average end. And this is because, after all, you have 5 hours instead of four. So the problems they picked are different. And I think and also like it's very important to make good observations for all these problems. For instance, analyzing the casework on when the expression can be evaluated to true in problem one, or noticing all these useful observations on problem three. Um, making good observations and making progress on the problems is also an important part of this contest as well. And I think if we were to generalize the entire USCO season, most of the problems throughout the season or most of the contests throughout the season have really followed the idea of one easy problem, one like moderately difficult problem, and one extremely difficult problem. And I think that USCO is getting less and less afraid of making bronze people write long code. Even though, of course, what long is relative, to speak. But yeah, I think that's something to keep in mind. And as for practice is concerned, especially for problems like problem three from this contest, I'd recommend just doing problems off code forces. There's a lot of there's a lot of problems that on code forces that are like relatively speaking ugly. They're not clean to solve. They're not necessarily enjoyable to solve. But I think USCO is also moving away from problems that are clean to solve and beautiful to solve. So you can prepare for that by practicing on judges like that. So I think that's all for the bronze session. Someone from CPI or Charlie Washer would like to add something else. Um, yeah, but that's it from me.